Well, folks, today I'm going to show you how to mathematically analyze these circuits without the use of the FET simulation. But I've drawn this circuit here in FET. I can toggle back and forth between. So there's you can see the electrons moving through. But this is what the circuits look like in textbooks. It's what they look on exams, what they look like on exams. And so you kind of have to get used to that. It's really nice that FET allows us to go back and forth between those two orientations. So I've taken that circuit, and you'll notice here that the numbers I have, they're not nice ratios of each other, so you can't really predict easily what's going to happen. But I have the circuit set up here, so 12.5 volt source. And, one thing that maybe you don't remember is that let's see here, now I got to get this, oops. Get the draw feature back up there. Like so. See if this works. All right, back in business. So you can see here, this is the exact same circuit that I showed you on the other side. This is the positive. Seriously, this is the positive. There's the negative. The long stick represents the positive end of a battery, and the short stick represents the negative end of a battery. That means the current is going to flow in this direction. Now, again, like if you had this on a test or an exam, this is what it would look like, and you would be expected to understand that this is the way that the current flows, right? So it's going to split there, and then it's going to reunite here, and then flow around, and back it comes. So there's the complete circuit, like so. Right? So that's the way that the current is going to flow. Now, I know that my total voltage, is 12.5 volts. In order for me to find out, number one, what I want to do is I want to find out what is the total current that's flowing through here. Like, what is the total current that's flowing through there? And I'm going to make these numbers bigger because I can't really see them. So there's 8.2. This is 14.5, 24.6, and there's 12.5 volts, like that. There we go. So now it's a little bit easier to see. I want to know, what's the current that's flowing through here? Well, I don't know unless I find, number one, you want to find the R total. You want to find the total amount of resistance that's in this circuit, and then you can find the total amount of current that's in the system. Well, I'm going to call this R1, call this R2, call this R3, and R2 and R3 are in parallel with each other. So what I want to do is to kind of collapse those two down and find out what is the equivalent series resistance that those two resistors possess. So I had to use this method. 1 over R parallel equals 1 over 14.5 plus 1 over 24.6. And I can do all of this in one step on my calculator, right? I mean, you don't need to do this manually. You don't need to find, and obviously, you're going to have a hard time finding lowest common denominators here and doing this by hand. So I'm just going to go 1 divided by 14.5 equals plus 1 divided by 24.6 equals, and I get 1.09 times 10 to the negative 1. And then I'm going to flip that upside down, and I get 9.12 ohms. So the total amount of resistance here, 9.12 ohms. Well, that's between the two of them, right? So the R parallel is going to be 9.12 ohms. And that means that the R total, so now it's like I have a 9.12 here, and I'm going to combine that with the 8.2. So it's going to be 9.12 ohms plus 8.2 ohms, which is 17.3. 17.3 ohms is the total. So now that I've got the total amount of resistance that's in that circuit, I can find the total current. The total current is the total voltage divided by the total resistance, which is 12.5 volts over 17.3 ohms. And that's going to give me 12.5 divided by 17.3 equals 0.72 amps. 0.72 amps. I'm going to change the color here now for my box. Now, because I'm smart, I have this circuit already up and running, and now I can check my answers. Every year when I do this, I ask students when they're working on these things, well, just build it in PhET, and then you can check and see if you got it done right. Sometimes students take me up on it, but not often. So here we go. I'm going to change this around so I can see what's happening. And, oh, look, I have the current thing all set up. And now let's look at the total current. What a surprise. 0.72 amps, which is what I got from my calculation. So that makes me feel pretty good. Now I can see that I've done this calculation correctly. So the next thing I want to do is find out what is the voltage drop across the series resistors. In this case, right, so this would be your very next step. I want to find out, so I'm going to call this number 3. Oops, call it 3. So I'm going to find the voltage drops across the series resistors. So in this case, I only have one resistor in series, and this is the equation we use. V is equal to IR. Okay, so we only have I is equal to V over R, V is equal to IR. It's the same equation, right? It's just rearranged. This is actually called Ohm's law. Now, I don't know if I've told you that before, but this is the equation that governs the current in DC circuits. Ohm's law, and the unit of resistance is named after Ohm, the same person who came up with this law. So now I can look at R1. So V1, which is the voltage drop when the current goes through R1, is equal to the current that's flowing through it. The entire current is flowing through. V is flowing through R1. And I multiply that by the resistance, which is 8.2 ohms. And that means that the voltage drop across, so when a coulomb flows through there, we're going to get 0.72 times 8.2. So we get 5.9 volts. So that is the voltage drop across this resistor, 5.9. Well, I wonder, is that done right? Well, there's an easy way to find out, isn't there? Let's go back here. And now I've got my voltmeter, and I can stick my prongs on here. So the negative that way, the positive that way. And, well, that's great news. So 5.9 volts is the voltage drop across the 8.2. So far, so good, right? This is conforming to what the simulation is telling me, right? Because the person that programmed the simulation, they're doing the same thing that I'm doing here. Like they're applying the rules that I'm teaching you to programming the simulation. Now that I've got that done, so if there were another resistor in series, we'd have to find out what the voltage drop across it is. And so once you know what the voltage drops are across the resistors in series, then whatever voltage is left over must be the voltage drop across the parallel branches. So I'm going to write that out. So number 4. So what you want to do is, in order to find the voltage drops across the parallel resistors, subtract the voltage drops of the series resistors from the total. So now the V of 2 and the V of 3, remember, hopefully I don't have to convince you of this anymore. The voltage drop this way and the voltage drop this way, they have to be the same. These are two different ski runs, but they both end up in the same place, right? The amount of energy loss going this way or this way is balanced. A circuit will balance itself such that the energy loss, no matter which path you take, is the same. And the circuit balances itself out by shifting the current. So here, like if you're going through the lower resistor, you're going faster. If you're going through the higher resistor, you're going slower. And what ends up happening is the energy loss is balanced. It's the same in both cases. So here, the V2 will equal the V3, and it's going to be the total voltage minus the 5.9 volts we found, which is lost as you go through the series resistor. So the total voltage was 12.5, and we're subtracting the 5.9 volts, and we get 6.6. So that means that the voltage drop across our parallel resistors must be 6.6 volts. Well, there's an easy way to test out and see if that's true, because I have this circuit all set up. So now let's go across this one, 6.6, and if we go across this one, oh, I'm supposed to have the black one down here and the red one up here, 6.6. So it doesn't, right? And if I had another branch in here, if I had another parallel branch in here, it would still be 6.6. Well, actually, no, because, well, my current would change, but the voltage drop across, no matter how many parallel branches I put in here, no matter what values I give the resistors, I mean, and you can try this if you like, the voltage drop across all of them will be the same. So now I know the voltage drops across all the resistors. Deadly. So the only other thing left to do here now is to find out what is the current in these two parallel branches. And so that's my only thing left to do. So number 5, what is the I2 and I3? Because you know that the current is going to split. Well, the I2 is going to be V2 over R2, which is, the V2 is here, the 6.6 volts. That's the voltage drop across that resistor. And the resistor itself was 14.5. And that's going to give me 6.6 divided by 14.5, 0.455. 0.455 amps. Supposed to be a thing here. And then I3 is going to be V3 over R3. The V3 was also 6.6 volts, but the resistance here now is 24.6. 24.6 volts. Ohms. So that's going to be 6.6 divided by 24.6, which is 0.268. So 0.268 amps. And let's go back and check the simulation and see if that's actually the case. Now, these are, it's going to round off. This is going to be 0.46, and this is going to be 0.27. So let's have a look in the simulation. 0.45 and 0.27. Okay, so it's rounded a little tiny bit differently. 0.45, 0.27. Maybe I rounded differently in my, right? So 0.45, 0.27, but very good. Well, the other thing here, and I'm going to create some space. This is something that I alluded to yesterday in the notes that I gave you. But the other thing that I haven't really discussed with you, like in person, is this whole business of power. And so I'm going to start this notes here. And so this is power. And the definition of power is voltage times current. So remember, voltage is how hard the charge is being pushed, and this is how fast it's going. So a really hard push and a really high speed is going to give you more power. So the total power in the circuit is going to be the 12.5 volts. So the total power of the source, which is, in this case, it's the battery, is going to be 12.5 volts, and the current that's flowing through it is 0.72 amps. We already discovered this, right? So the total power is going to be 12.5 times 0.72, which is 9 watts. 9.0 watts. That's the unit of power, right? The power in your home. If you've got a 1500 watt hair dryer, it means it's converting 1500 joules per second. So remember, your 1 watt equals 1 joule per second of energy conversion. By definition, that's what power is energy conversion per second. Well, now we can look at the power of each one of these resistors. So I've got 3 resistors, and what I want to know is, what is the P1? It's going to be V1, I1. What is the P2? It's going to be V2, I2. And what is the P3? It's going to be V3, I3. So in the first resistor, we have the voltage across this one, we found that one was 5.9. So this is a 5.9 volts across here. And the current flowing through it is 0.72 ohms. So the power of my 8.2 resistor, this is how much energy it's converting, times 0.72 is 4.25. 4.25 watts. That's how much energy is. So here, energy is being created or it's being given to the charge. Here, the energy is being used by the charge to do some other kind of work. And then for P2, that's going to be, we determined that the voltage drop across the other two was, it's gone off the screen here for some reason. Let's see what's happening. Oh, we have technical difficulties here. Oh, there we go. 6.6 volts. I'll make this a bit smaller. Make sure everything gets on the page. There we go. Now it's all on the same page. So for our power, V2 was 6.6, and the current was 0.455. So here it's 6.6 volts and 0.455 amps. And that's going to give me 6.6 times 0.455, and I get 3.00. 3.00 watts. That's through the second resistor. And then through the third one, we also have 6.6 volts, but now the current is 0.268 amps. 0.268 amps. And when I do that out, 6.6 times 0.268, and I get 1.77. Or 1.77 watts. And when you do this, for all of the resistors in your circuit, the P1 plus P2 plus P3 equals, well, you can kind of do this in your head, can't you? 4.25 plus 3 plus 1.77 is 9.0 watts. So the power of the source was 9 watts, and the power dissipated by all of the resistors in the circuit is also 9 watts. When you do your circuit analysis, This is how you know you've done it right, because all of your power ratings for all of your resistors come out to equal the power of your source. So just to recap what we've done, okay, here's the steps. There's a circuit. We have the total voltage. We found the total resistance by combining the parallel branches and then adding the equivalent series resistance of the parallel branches to the resistor in series. And that gave us the total resistance of the circuit. Once we have the total resistance, divide the total voltage by the total resistance, and we get the total current. That's what's flowing through, the series portion of the wire, 0.72. Once we know how much current is flowing through the series resistor, we can find the voltage drop across the series resistor. And if there were more than one, we would do this, for each one of them. The voltage drop is current times resistance. We know the current, we know the resistance, and we know the voltage drop across R1. Now all we have to do is subtract that voltage drop from the 12.5, and that gives us the voltage drop that must occur across R2 and R3. And we found that it was 6.6. And our FET simulation indicated that was correct. The voltage drop here and here is 6.6. Now that we know the voltage drops across those two resistors, we can calculate the current in those two resistors. The I2 is the 6.6 volts divided by its resistance, 0.455, and the voltage drop across the third one is 0.268. And that was also confirmed by checking in the FET simulation. So now we had the circuit completely analyzed here. And now we can check the power of the source, the power of each resistor in the circuit, right? So there's P1, that's the power of R1. I probably should have written this in here. So there's the R1 power, and this is like the R2 power, and there's the R3 power, like so. You just calculate the voltage of R1, the current going through R1, the voltage of R2, the current going through R2, like that. And then when you find the three powers, and if there's more resistors, you just do it for each one. Voltage of that resistor multiplied by the current going through that resistor gives you the power. How many watts, how many joules per second are being transformed into some other kind of energy as it flows. And, a lot of times it's heat, but it could be anything else. 9 watts, 9 watts. Folks, that is a complete analysis of this circuit. We found everything. We know the voltage drops across all the resistors. We know the current in all the resistors. We know the power of all of the resistors. That's a complete analysis. And what I want you to do is to, that sheet that was handed out yesterday, I don't know how far you got with that. I have a feeling not very far. But now you have the tools to do this same process with the sheet that was handed out yesterday. Okay, so if you need, I'm going to save these notes and post them so you can have a look at it, but you can also watch the video and freeze frame and rewind and put it wherever you want and review it at your heart's content. And hopefully you're going to find this helpful in your work today